field on Wikipedia. Over hundreds of years, magnetic declination is observed to vary over tens of degrees.
Nice.
Oh well. Let's just pretend it's 20-something degrees, but it's something. Okay. So again, if you follow your compass, just keep going north and north and north, you're going to miss Santa's house by like 20-some degrees. Okay. Electrons and magnetic fields, this is what I was talking about before. This is how old televisions used to work and old computer monitors used to work. They had something called an electron gun, and they would fire particles. Pew, 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 pew. They would fire a little electron pew, 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 at a screen, and the screen would light up when a particle hit it. So basically the screen was given a hugely positive charge, and you fired electrons at it. Pew, 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 pew. They're attracted to the screen. And then you had a magnetic coil that would constantly adjust itself to paint the picture on the screen. It would be like, okay, this particle needs to go there, boop, pew. This particle needs to go there, boop. Change the magnetic field. This particle needs to go there, boop. This particle needs to go there, boop. And it would constantly do that billions of times a second. It would just constantly change, and it would paint the screen 30 times every second. Paint, 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 paint. And that's how it worked. Yeah. Nowadays, they just have little LEDs that light up into with green, blue, and red light. But yeah, that's how it used to work. So, magnetic fields are measured in Teslas. A single Tesla is a tremendous amount of magnetic field. Big, huge MRI machines, like as big as this desk, are usually measured in single or tens of Teslas. It would not be unusual to go to the hospital and it's like, what's the force of this magnet? You're like, it's 4 Tesla. You're like, 4 Tesla! Yeah. A single Tesla is a tremendous amount of magnetic strength.
Croatian.
Yep, Nikola Tesla was a Croatian American. Yeah, was or is a country called Croatia. It's next to Bosnia, or was next to Serbia, Eastern Europe. There was a war that we fought in the 90s because this guy named Slobodan Milosevic was trying to kill all the Croats. So we dropped bombs on him from the stealth bomber. It's the first time the D2 Spirit stealth bomber was used. We launched him from Missouri, and then he's like hanging out in his little bunker. He's like, nothing over my skies, I'm good. And then his bunker exploded. Yeah, that's what we got. We got the D2 stealth bomber. So moving electrons create magnetic fields, and changing magnetic fields create electrons. And here is the formula. Formula number 1, formula number 2. F. Force, and it is a vector, equals QVB. Q, ooh, that's a terrible Q, let's try that again. Q, V, B. Vector, vector, vector. Now we have an issue. What is the issue? The issue is this. If you multiply a vector by a vector, you get a vector. If you multiply a vector times a scalar, you get a vector in the exact same direction. If you multiply a scalar times a scalar, you get a scalar. If you multiply a vector that is right multiplied by a scalar, you get a vector that is to the right. If you multiply an upward vector by a scalar, you get an upward vector. But what happens if you multiply a vector that is to the right by a vector that is up? You get a vector in the 3rd dimension. You get a vector that is that way. If you multiply a vector that direction by a vector that direction, you get a vector that direction. 2 vectors, 90 degrees to each other, will produce a 3rd vector in a 3rd dimension. That's why we have a right hand. Right hand. Does everybody have a right hand? Okay. So if you don't have a right hand, then you can use your left hand, but you have to remember the force will be the opposite direction. Your fingers, you have to pretend they're going the other direction. Okay. So hopefully everybody has a right hand. But that's how it works. That's the right hand rule. If you have a vector in this direction multiplied by a vector in this direction, you get a 3rd vector in that direction as its product. Yes?
What if you multiply it in all 3 directions?
If you multiply 3 vectors together?
Yeah.
I don't know. That would be a Strachan question, I think. I primarily focus on what I need. I don't focus on theories I don't need. I don't remember to multiply. All three. A single, if you had 3 vectors in all 3 dimensions, I'll look into it. Okay, so this is going to give you a formula. This is an interesting formula. What this means is this. Are you paying attention? This is the charge of a particle traveling in a magnetic field. This is the electron being launched from the electron gun and slamming into the phosphor screen in front. This is how fast that charge is moving. This is the magnetic field, and this is the force that it applies, or that it feels. Okay, does that make sense? You can also rearrange this way. If you apply a force on a charged particle in a magnetic field, that's how fast it's going to go. Okay? So you can basically say, this is the force that charge is going to feel when it's got a certain number of coulombs times a meter per second times a Tesla. That's the charge it feels. Or you can say, if you apply a force on a charged particle in a magnetic field, that's how fast it's going to go. Okay, make sense so far? Okay, next thing. If you have a charged wire, you run an electrical current through a wire. That electrical current, that flow of electrons, is going to create an electric field. That electric field is going to create a magnetic field. Okay, everybody say, yeah. Yeah. Okay, see what you're doing right now? Your thumb is the flow of electric field, or electric current. Your thumb is the flow of electric current. Your fingers are the magnetic field. I'm going to use my pipe as a giant wire. So let's pretend there's marbles going down the pipe like electrons. Your thumb would be the direction of the flow of charge, and your fingers are the magnetic field. You imagine spirals of magnetic field around? Spiral, 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 spiral. Okay? Does this make sense so far? Okay. So, above the field, above the wire right here, the magnetic field is going where? It's coming towards you. And below the wire, it's going away from you. So it's basically going spiral, 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 spiral. So the magnetic field is going around and around and around. So if this is the current here, out here it's going toward you, and here it's going away from you. The magnetic field is going towards you here and away from you here. Another name for toward would be toward. Don't do anything toward. This would be out of the plane. And the current here would be away. Or sorry, the magnetic field would be away. This would be into the plane. So current is traveling down the wire. Imagine there's a wire just up to the whiteboard. Current is traveling down the wire. The magnetic field is coming out of the plane above the wire and into the plane below the wire. Now, how do we show this? How do we represent a 3-dimensional phenomena on a 2-dimensional piece of paper or a whiteboard? Use an arrow. So, the front of the arrow looks like what? A ball, or in 2 dimensions, it's a circle. And the back of the arrow looks like a what? It's an ellipse. You're not holding it perfectly. And the back of the arrow looks like it's only got 3. My arrow here only has 3 sides, but most arrows have 4. So imagine an arrow has the fletching in the back. Those are the feathers. So when a vector comes at you, we give it a dot. So when a vector comes out at you, we give it a dot. And when a vector is moving away from you, we give it an X. Okay. So out of the plane is a dot, like an arrowhead coming right at you. And away from you is the fletching. I don't have a 4-sided arrow. I just got to go to Hunter's. I got to go to Hunter's warehouse and like, give me an arrow. We only sell them in packs of 50, so you can kill something. Sorry, I just want to show somebody. Okay. So, if we were to draw the magnetic field here, what we would do is we would show it with a series of dots. These dots represent an out of the plane magnetic field. And into the plane, we would show it with a bunch of X's. They represent an into the plane magnetic field. You always use your right hand, by the way. Into the plane magnetic field. So far, so good? Now, this is I. Let us show I with a dot. If the magnetic, imagine a wire going this way. Imagine a wire coming out. Actually, just use this. That's a wire. Okay. Imagine there's current traveling into the plane, which would be an X. Current's traveling into the plane. So now we are. Current's traveling into the plane like this. What direction is the magnetic field going?
Away from
It's going around. It's going like this, right? So if the current's going this way, then the magnetic field would be going in a circle around that way. So if the current was going into the plane, the magnetic field would be going around it. Does that make sense? Feel free to use your finger, your hands. You're like, get into it. You're like, okay, I can see it doing this thing. Yeah, right, cool. Now on the other hand, if the current was coming at you, now it's coming at you this way. Current's coming at you this way. Can you tell what direction the magnetic field is going? Going this way. Now the magnetic field's going that way. If the current's going at you, the magnetic field's going around this way.
Oh,
That.
go get it.
Oh, okay. Whatever. Okay.
There was a vector.
It was something. Okay, next equation. Now that we know the direction, we're almost done for today. Now that we know the direction of magnetic field, its strength around a current carrying wire is given to us by B equals how much current you got over how far away you are from the wire. Multiplied by some constant that basically says this is how good that material is at carrying a magnetic field. So the magnetic field strength that is produced by a current carrying wire is proportional to how much current the wire is carrying and inversely proportional to how far you are away. The 2 pi has to do with the circularness. And then multiply, and it's also proportional to some kind of constant that says this is how good the material is at carrying a magnetic field. How are we doing?
Pretty good.
Okay, are we good to stop?
I have a
Question.
question. How do magnets bring electrons?
I'm sorry?
How do magnets bring electrons?
They make the electrons go where they should not go, which tends to make them pile up. It's kind of like, you know what hose, you've heard of kinking a garden hose?
Yeah.
Okay, you take a garden hose and you kink it, and basically the water piles up. Okay? Now imagine your hose was only so strong, and you kinked it, the water would pile up and then burst. So that's what you're basically doing. You're basically saying, okay, electrons, stop here. And the electrons are like, okay, but I still have to move. So they keep moving, and they warm up the material, warm up the material, warm up the material, the material fails.
Why exactly does